Repeating the operation until all of the joints are desoldered. Hopefully the component should come out of the board without any difficulty. Remember never to pull it with any force. As you can see, this process can take a while, and the same damage can happen similar to axial components, except that there are a lot more opportunities for things to go wrong. That's because this dip component has 14 leads, whereas an axial component has only 2. When unclenching the leads, you can inadvertently tear the land away from the board or gouge the board. Staying on the connection too long can result in measles, burns, and delamination. And there can be the dreaded sweat joints. If you try to remove the component with force, you can damage the whole wall. So when the component doesn't come out easily, you'll need to figure out which leads have sweat joints. You can do this by gently moving each lead until you find the one that doesn't move back and forth. Then we'll add solder to that particular joint in order to transfer the heat all the way through the hole. Always give the joint a few seconds to cool off after you add solder to avoid overheating the hole. Now you can desolder the hole once again, and the dip should be ready to come out. You can see how time-consuming this process can be, along with the possibility of causing damage to the circuit board assembly. Now we'll examine Ray's secret. In the same manner as the process we've just seen, the first step is to straighten the clenched corner leads. Again, this needs to be done carefully. Next, we add solder to the leads. Then we use these thermal tweezers to heat the solder and remove the component. Pretty simple, isn't it? Now we complete the process by cleaning the holes with the vacuum extractor. At this point, you're probably wondering why we didn't just cut the dip leads the way we do for axial components. Let's try it and see what happens. It's not so easy, is it? And there's a good possibility you'll destroy some lands in the process. Through-hole connectors are similar to dips in that they are multi-lead devices, often having as many as several hundred leads. Many of these connectors are not configured to allow the use of Ray's heat and tweeze method that you observe for dip components. For large connectors, we can use the solder fountain. It has the same advantages as the previous secrets, but on a much larger scale. The conventional method of removing these components is the same as we saw for dips. It can really take a long time to remove one of these high pin count connectors. And there are even more opportunities for things to go wrong. Now let's examine Ray's technique of using the solder fountain. Once the fountain is running, all you have to do is heat up the connection area until the solder melts, then remove the connector with a set of pliers. It's really that simple. Then we finish the job by clearing the holes with a vacuum extractor. The solder fountain technique does have some risk. There can be copper dissolution caused by the flowing solder bath. Copper dissolution is caused when the tin in the solder dissolves the copper on the land areas. This means that the longer the area is left in contact with the flowing solder, the more copper will be dissolved into the solder bath, causing the copper on the lands to become thinner or to disappear completely. Lead-free solders with their high tin percentages are even more aggressive when it comes to copper dissolution. Obviously, minimizing the exposure time to the flowing solder will reduce the copper dissolution. This can be accomplished by preheating. Preheating can be done as a separate step or as an integral part of the solder fountain component removal process. In this manner, the flowing solder is being used to remove the part and not to heat the assembly. When preheating tin lead assemblies, a topside temperature of 100 degrees C is recommended. When preheating lead-free assemblies, the recommended topside preheat temperature is 150 degrees C. It should be noted that it is much easier to control copper dissolution through the use of preheating than it is to control a technician trying to manually desolder 100 or more individual solder connections. The biggest risk when doing surface mount rework is lifting a land. In many cases, surface mount rework results not only in land lifting, but in complete removal of the land from the board. The reason that this type of damage occurs more frequently on surface mount versus through-hole rework is that surface mount lands are typically much smaller. This means they have a much smaller area of contact for each lead compared to a through-hole land. The failure occurs when the application of heat causes the material that bonds the copper to the board to become soft or over-cured and loses its adhesive strength. That condition, coupled with the pressure and slight movement of the soldering iron tip, can cause the land to break free of the substrate. We'll start by examining the removal of low thermal mass surface mount devices such as a multi-lead QFP. The traditional method for removing these components is to use a special tip that heats up all the leads at once. This method works great if the technician is very skilled, but can result in lifted lands if performed by less skilled rework technicians. Ray's secret is to use convective or hot air removal techniques, which are much safer when performed correctly. Let's begin by reviewing the typical technique for removing a QFP using the thermal tweezers. We always begin by making sure that the tips match the size of the component. Remember that we want the tips to rest on the feet of all four sides of the leads. After the proper tips are selected, we install them in the handpiece. Squeeze the tips together to ensure alignment, then tighten the set screws. The larger tips will require a special alignment tool. For the larger QFPs, we may want to use a thermal enhancement technique, other than flux, to further speed up the removal process. The solder wrap or solder preform process is designed to help improve the heat transfer. We begin by tacking one end of a solder wire to one of the corner leads. Then we wrap the solder tightly around the component right at the heel of the leads. You'll have to experiment with the size of solder wire to find out what works best for each component. After you've selected the correct size tip and cleaned and tinned it properly, you may also want to add external flux all the way around the component. This will help improve the heat transfer. Now you're ready to position the tips on top of the solder prefill. Gently tweeze the component with the tips. Then, after you see that all of the connections have melted, lift the tool straight up. Then place the component onto a heat-resistant surface. Next, let's examine the problems that can happen when a less skilled technician uses this technique. As you can see, applying too much pressure and rocking the tip around to melt the solder can result in lifted lands or bent leads. Now we'll take a look at what Ray recommends. A rework station is the safest convective or hot air removal method. Some rework stations are very sophisticated, removing and installing components using full-blown thermal profiles and automated vision systems. Medium technology stations also provide for safe component removal and are much more common in facilities. A much lower tech process is using a hot air gun. However, it does require a rework technician who is able to stay alert and avoid distractions. When it comes to high thermal mass surface mount components, Ray also recommends convective removal methods. That's because it's difficult to apply enough heat to the connection area without increasing the tip temperature and taking the risk of burning the board. The only way to properly use conventional techniques is to preheat the assembly, especially when reworking lead-free assemblies due to the higher solder melt temperatures. Here's what happens when you don't preheat the assembly. Now let's watch how fast and simple Ray's method is. Our final topic for surface mount rework involves ultra-small surface mount devices. The big difference in reworking these ultra-small SMT devices is that they are a lot smaller. This means we'll need greater magnification to see the soldering operation clearly, and we'll need tools that are appropriate for the size of the devices being soldered. You can see that removing or replacing a multi-lead fine-pitch QFP is the same if we use proper magnification and very small soldering iron tips. When removing or replacing chip-style components, the old tweezer tips are too large. With magnification and soldering iron tips with very fine points, it is not that difficult. This video has presented Ray's rework secrets. We've examined the removal of through-hole components such as axial resistors, dips, and multi-pin connectors, and surface mount components using convective methods. We also explained what's required to rework ultra-small components. Effective rework requires educated decisions. There are many different factors to consider for each different situation. If you have any questions about whether to rework or which rework technique to employ, don't hesitate to ask your supervisor. Asking shows that you really care about what you do. And Ray's secrets should make your job safer and easier.